And everybody's kind of stuck with me this long. I just spread misinformation, but at this point, it's just people believe it, I guess, because I say it with force, you know, like I mean it. The thing about this particular class, I'm going to share my experiences as a contractor, things that we've run into, but I'm certain that the collective knowledge in this room is much greater than what I'm going to cover, and there's also probably some of you that your individual knowledge is probably much greater than me on this. So I'm totally fine with this being collaborative and you speaking up and that kind of thing, especially because of the numbers in the room. I'm going to bring up some points, some things that I think are really important to consider in terms of inverter-driven equipment. But the thing that sort of is a through line in all of this is that it's not, inverter-driven equipment is not just one thing. And so when we talk about even some of the stuff today, I got a chance to talk to Steve Rogers about some recent research that he's done. Chris Hughes has been doing a lot of interesting research on charging inverter-driven equipment. There's a lot of other really smart people who are doing this. And a lot of what well, actually, one of the best is Craig Miglaccio on the ductless side. He's done a lot of testing, but a lot of what we face here is that the manufacturers, they don't tell us the whole story, which is kind of a bummer. And so one of the things that hopefully we're going to see emerge is putting a little more pressure on manufacturers to be very transparent about what's going on with their equipment. So not only can we install it, but we can also select it better and we can service it better, because that's where there's some real consistent things on the installation side that you know if you do, you're going to get better outcomes. But there's a lot of things that are pretty tough to test in inverter-driven equipment, especially ductless, and sometimes system selection. There's some stuff that's missing. So we're going to talk about all of that to some degree. I'm not going to focus a lot here. But there are a couple interesting things, and one thing, I know there's a lot of you here who do a lot of speaking. Obviously, Ed does a lot of speaking, and if you ever go to I don't know why anyone would come to this class if you went to the one the other day, but if you happen to, you're going to notice that this is going to be a lot different. Every time I give a class, I just new things kind of pop into my head based on the feedback and all that, and so we're going to cover some different stuff here. But even inverter-driven doesn't always mean the same thing. So fundamentally, what is an inverter? An inverter is just taking alternating current, an analog sine wave, and turning it into some kind of version of DC. It's usually not perfect, but something that then can be controlled to spin motors at different speeds. That's what we're trying to do. The outcome is we're trying to spin motors at different speeds. There's a lot of different ways of doing staging of equipment, capacity control of equipment that does not involve spinning motors at different speeds. And so that's where sometimes people will get a little confused. They'll say I'm gonna go down a stage, or I'm going to on the opposite side they'll say I'm gonna reduce the speed of the compressor, but it's actually just a multi-stage compressor. So don't confuse multi-stage equipment with inverter-driven equipment. Those are two different things. The other thing is a lot of people want me to teach them how inverters work, like so break it apart and like show you the insides. And in residential, that's just not that valuable. I mean, it's very interesting, and I'm fascinated by it, but it's just not that valuable, and it would take weeks for us to really do justice to that. And so that's not really what I generally teach. It's similar to like when a lot of techs will say, we really need to learn how to read diagrams. We need to learn how to read schematics. Well, do you know the best way to learn how to read schematics and diagrams? It's to actually do it. Like you kind of have to do it in real life, because I can show you some common symbols and I can get you kind of oriented to where things are, but ultimately you're going to need to read the legend and you're going to need to read the notes, and so when I teach it, that's what I teach you to do first. And then you're going to need to go left to right, top to bottom, and you're going to find things you can identify and go from there, but you're ultimately only going to learn it when you're solving problems with it. And that's the same thing here. It's like you're going to find things that are common issues with inverter-driven equipment, and then that's going to drive you to understand it more deeply, because you need to know those things in order to solve those problems that you're facing, if that makes sense. And because none of us are going to get an engineering degree in electronics, right? None of us are going to become, get a degree in computer science. And really, in order to truly understand everything that goes on behind this, you would have to understand some of that stuff. So trying to keep it pretty simple. One thing I do want to mention here, though, anybody here ever work on a true variable frequency drive, like a drive that's actually external to the equipment or separate to the motor, right? There's a difference. This isn't the same thing. So a lot of what we think of when you're in that variable frequency drive world, and we do a lot of work in grocery stores, so we do a lot of rack refrigeration, and in that world, there's a ton of variable frequency drives all over the place. With those type of variable frequency drives, external to the equipment, what they're trying to do is take a motor that was designed for alternating current and spin at different speeds, right? So you're actually changing that frequency away from 60 hertz or 50 hertz if you're, from one of these other countries we don't care about. This is America, 60 hertz over here. Gosh darn it. Where you're trying to take that 60 hertz and you're trying to change it in order to spin things different speeds, right? And when you're doing that with motors that were designed for alternating current, you use a very different type of strategy to spin the motors. If you look at the way that the pulses look, for example, and this is what Steve Rogers and I were going over, and it's really fascinating, how they work with, say, a ECM blower. Now again, when we're talking about inverter-driven equipment, we're not generally saying an ECM blower. But an ECM blower is an inverter-driven motor. That is what it is, right? It has an inverter, it has a drive on the back of it that controls the speed of that motor at varied frequencies. Everybody get that? Even an X13 or whatever we're calling it nowadays, constant torque motor, is a variable frequency driven motor. But it's different in that that motor was designed to run with that drive. So it really is, it's a permanent magnet rotor motor, and you don't need to have these really weird pulses that we run if you work with a regular variable frequency drive. So with a regular variable frequency drive, what you're doing is you're creating these peaks that are supposed to sort of simulate a sine wave. So at first there's fewer of them, and then when it gets into the middle there's more, and then there's fewer, and then there's more, and you're kind of simulating this analog curve. But when you're doing it and it's designed for it, and this is true of a lot of the compressors we see today too, because you'll hear sometimes they're like, it's a DC compressor, it's a brushless DC, it's a three-phase motor that's like, all of those are kind of saying the same thing, but their question really is, was it designed for it initially? Was it made for these two things to go together, and so it can be a little simpler? Or are you trying to drive a motor that was designed for alternating current different speeds? Does that make sense? And so when we say variable frequency drive, or in refrigeration we call it a freak drive, which I think is really cool, by the way. F-R-E-Q drive. You never heard that before, Ed?
No, that's pretty cool.
It is pretty cool. And so,
it sounds really cool when you say it.
Like, I really think I want to say, instead, I don't want to say inverter driven anymore. I want to say this sucker's got a freak drive on it. Yeah. And then it sounds like really awesome, like something, yeah, super cool is happening. So again, pulse width modulation simulates three-phase power, and we'll say that. We'll say like, oh, it's a three-phase motor. Well, sometimes, but sometimes not. Sometimes it's actually a motor, it's kind of three-phase, but it's specifically designed for this drive to be on it. I'm not going to belabor this point, but there are these variations, and it's not like you go to the manufacturer and they explain that to you. You know, they just use, like, yeah, it's got, all this turn down capacity and whatever, but they don't explain how their software works, and they don't explain how it's programmed, and they don't explain how it's going to behave across this entire range of operation. So we have to kind of figure that out. And it's good to know this about your equipment. And we'll talk about why. All right, so what are some of the inverter-driven system advantages? Well, Jim Bergman, when he saw that I was going to talk about this, he said, and I quote, "Inverters are the most amazing technology that I've ever seen." And I was thinking to myself, like the wheel, maybe the screw, I don't know, but no, it is a really amazing technology because it can do really neat things. And what he was pointing out is that he now uses an inverter-driven heat pump in conjunction, dual fuel in conjunction with a gas furnace, and he's just getting really great results out of it. And that's what a lot of people will notice first. If you're in a cold climate, they work a lot better than they used to work. People who used to hate heat pumps now are like, hey, they do pretty well, right? And let's just pause a second and talk about why that is. Why, all of a sudden, do inverters make cold climate heat pumps possible? Any major theories that pop in anyone's head, or anything you want to add to that? Why do they make it possible? There you go. You can spin the compressor faster. So you can take a compressor that previously was 36,000 BTUs, whatever, and you can spin it faster. You can pump more refrigerant, right? Now, is that a good thing? Well, no, it's not a good thing unless you need to do it, right? We don't want to spin motors faster unless we need to spin them faster. Let's go back to ECMs, okay? Because there's a correlation here. When ECMs first came out, does anybody remember like some of the first generation ECMs, some of the first generation variable speed blowers?
Yeah, the ICM.
Yeah.
Predated the ECM, sure.
When they first came out, at the time I was working for a train dealer. Well, I mean, it was a little before me, but at the time when the kind of first generation was out, we had blower wheels that were just blowing apart. Like just literally, you'd have blower wheels failing all the time. The train blower wheels, they'd go like this. They'd puff out and they'd stop attaching in the center hub. And the reason that is because when you put these air handlers on bad ductwork, what would they do? They would just keep spinning faster and faster in order to try to achieve the airflow, right? Is that a bad thing? Well, yeah, because it blew itself apart, right? That's the reason it's a bad thing. But is it a bad thing that it was trying to do that? No, it makes sense, right? Now, what should we have done to solve that problem? Well, you don't put it on bad ductwork, right? That's not, you don't try to use an ECM to solve bad ductwork.
But your GM was telling you guys exactly why you should put it.
Exactly, it's going to solve all the problems, right? And the same thing is true of dehumidification even today. People will say, oh, these are amazing at dehumidifying. They are just the bee's knees at dehumidifying. And it's funny, you pull out this old stinky 8-seer ream with the dirty evaporator coil, and you put in a brand new inverter-driven variable speed Bosch or whatever you pick, right? And all of a sudden the humidity's higher in the house. And what we tell the client is that they're just crazy. But they're not a lot of times, and there's reasons for that, and it comes down to what are you trying to accomplish, right? So if you are trying to accomplish overcoming bad ductwork by spinning a blower faster and you don't do something about that, then you're going to have major problems. Here's the same thing with cold climate heat pumps, okay? If you took a normal compressor and you just spun it faster, you're increasing the compression ratio significantly. You're going to burn that thing up. You're going to have massive discharges, you're going to have massive compressor head temperatures, you're going to have massive discharge temperatures, you're going to destroy the oil, you're going to destroy the compressor, right? So you can't just take a regular compressor and spin it faster. You have to take a regular compressor, spin it faster, and do things like vapor injection or other design changes in order to be able to get that increased capacity out of the same compressor. A compressor that's going to do the job in cooling and not be massively oversized, but then when it's time for heating, you can just wring a bunch of BTUs out of it because you're really spinning that compressor fast. Does that make sense? So that's why, that's all it is. Cold climate heat pumps are two main things together. You take a variable speed compressor, an inverter-driven compressor that you can overclock. This is a term from computers. I like to think you're just overclocking it. You're spinning it faster, and you have these other design changes that allow you to keep it cool. So that way it doesn't become a problem. And this is not new. Like in market refrigeration and other places, they've been doing things like this. You know, interstage cooling and other things like this in order to manage compression ratios forever. This is not a new thing, but now we're just applying it to inverter-driven. What's the other good thing? Well, it's about load matching. We want to load match, which means that for every BTU that we're adding or removing from a space, we just want to supplement that BTU. We don't want to overcool, we don't want to overheat. Anytime you produce an energy state that's greater than is necessary, you're wasting energy. Right? So anytime you're making a space hotter than you need to make it or cooler than you need to make it, anytime you're making ducts hotter than you need to make them or cooler than you need to make them, anytime you're doing that, you're wasting energy. So the more you can load match, the better you're going to be. And inverters do a really good job of that. Why? Because they can spin things different speeds, right? Because that's good. There's some other issues though. So part of the issue is that oil return can become a problem. Because now you had a system that was designed, you know, all of our piping, everything that we've ever done was designed for pretty fixed velocities, right? Pretty fixed mass flow rates through these lines, and now you're varying it a lot. So you have to think about, you don't want to put something in that's going to be really improperly sized, that it's going to be turned down all the time, meaning it's going to be running real slow all the time, because you're going to have oil return issues. Now manufacturers like VRF, VRV, where they have miles of copper all throughout the building, they have to figure out ways to mitigate this, where they drive it into high speed and they get the oil back to the system, or they pump some liquid through the lines in order to get it back. So there's these kind of technologies that you have to deploy, but these are challenges, these are design challenges, and sometimes the manufacturers do a really good job with it, and sometimes they don't. Here's another one, dehumidification. Theoretically, a inverter-driven system should be amazing at dehumidification, okay? Anybody here who does not care about humidity in their market, like humidity is not even a concern? Which market is that?
Bend, Oregon, zero latent load.
Yes, absolutely. It was funny, I got asked to go to Seattle to speak at a FIAS conference. And I was so excited. You know, I'd never been to Seattle before. You know, there's all these hippie nerds. I'm going to get to do this presentation that I'd done a bunch of times, so I felt super confident. And I got up there and I was like, yeah, I got a bunch of dehumidification stuff in there. And they look at me like I have 3 heads and one of them's on fire. I'm like, oh, you don't do that here, do you? No. You know, this is, they said this is Goldilocks land. You know, it's like, you know, the porridge is just right, you know. Or I guess that's the baby bear. Yeah, it's baby bear land. But where I come from in Central Florida, and a lot of places throughout the Gulf Coast, any green grass climate, primarily, you have issues with moisture. There's 2 things you need to do in order to get moisture out of a space. You need to have long run times, and you need to have cold evaporator temperatures, right? Any evaporator temperature below dew point is going to pull some moisture. But the further you are below dew point on your evaporator coil, the more moisture you're going to pull. We all know this, right? You run your blower slower, run air over the evaporator coil slower, you're going to pull more moisture out of the air. You're going to wring more out, right? Okay, fine. So theoretically, an inverter system should be great at this, because what it should be able to do is when we turn the compressor down, when we spin it slower, right, because we don't need as much capacity, we don't need to pump as much refrigerant through the system, we should be able to just also slow down that blower at exactly the same rate, and then we always keep a same evaporator temperature. Does that make sense? You're pumping the same amount of refrigerant. If you pump less refrigerant and you keep the air flow the same, what happens to your coil temperature? Goes up, right? Creeps up on you. But if you drop your blower temperature as you drop your compression, then you should be able to keep that nice cold evaporator coil, maybe 38 degrees, 42 degrees, in that range, right? Where it's going to do a really good job of wringing moisture out of the air. The problem is that a lot of times manufacturers don't optimize for this. They optimize for compression ratio. Not going to go into compression ratio here, not too deeply. But what they're really optimizing for is energy consumption. So when you see a 30 SEER ductless system, I don't need to know anything else. I know that it's going to be terrible at dehumidifying at that 30 SEER. Because sensible BTUs are much less expensive to get out than latent BTUs. Warming an evaporator coil is a very energy efficient strategy, just like we talked about, right? When you make things colder than you need to, bad on energy. We don't want to make an evap colder than we need to unless we need to get moisture out of the space. And then we want to, and we just have to, because that's part of the deal. Make sense? So, inverter-driven equipment is very good at running a lot. That's great, thumbs up. We want equipment to run a lot. We want it to run all the time if we could help it, right? Unless there's absolutely no load on the structure. Downside is sometimes they're not great at keeping a cold evaporator coil when they've turned down, when the compressor's spinning slower. And that's something you need to know about your equipment. Problem is most equipment manufacturers don't give you data on how well they dehumidify when they're turned down. They give you when it's run in full bore, right? So you got to kind of do that testing yourself. If you're having issues with your equipment, if you're having issues dehumidifying, then that's what you need to look at. Get it turned down to where it's right at about set point, and then throw your 9 probes on it, look at measure quick and see how it's doing on latent. And that's sensible heat ratio, right? You want to see a sensible heat ratio that's nice and low. Generally speaking, if you start seeing it creeping above 0.8 sensible heat ratio, you're not doing much. It's not doing great.